Let's consider the following question, which at first doesn't seem to be particularly interesting, but which turns out to be important. Here I have two bundles. This bundle is 5,10 and this bundle is 10,5. I'm indifferent between these two bundles and there is an indifference curve containing both of these bundles. Now let's say that I double the amount of each good in both of these bundles. For the 5,10 bundle, doubling the amount of each goods will give me a new bundle, 10,20, right here. Doubling my second bundle, 10,5, will give me a bundle 20,10, which is located right here. Here is the important question. Will I be indifferent between these two new bundles? If I am, then preferences will be called homothetic. If I'm not, well, then they are not homothetic. Think about it like this. Let's say that we have two shopping carts, a blue one and a red one, containing different quantities of various goods. Suppose that you're indifferent between these two shopping carts. You find them equally nice. Now you're presented with the choice between two blue shopping carts and two red shopping carts. It's not unlikely that you will be indifferent in this case as well. However, it is possible for a consumer to be indifferent between the two initial bundles, but to find one of the new bundles strictly preferable to the other new bundle. For example, let's say that this is food and this is travel. And you're indifferent between the 5,10 and the 10,5. It could then be the case that 10 units of food is pretty much all you need. 20 units of food may be overdoing it. And you would rather have 20 units of travel and 10 units of food than 20 units of food and 10 units of travel. If that's the case, then the indifference curve through 10,20 will look something like this. And preferences are not homothetic. For homothetic preferences, I need to be indifferent between these two double bundles. And the second indifference curve will look like this. Based on this example of homothetic preferences, where I need to be indifferent between the doubling of two bundles if I'm indifferent between the initial bundles, we can create a definition of homothetic preferences. We can create a definition of homothetic preferences which doesn't rely on the specific choices of bundles I made here and the fact that I have doubled them. So instead, to make this general, our first bundle will be denoted by x1, x2, completely arbitrary. It could be, for example, this one. My second bundle is denoted by y1, y2, and that could be this one. So the definition goes, for any such bundles, for any x1, x2 and y1, y2, for which I'm indifferent. So I need to write for which I'm indifferent between them, x1, x2, y1, y2. The following must hold. When I doubled my 5,10 bundle, I ended up over here in my 10,20. If my first bundle is now arbitrary, this new bundle needs to be denoted by 2x1, 2x2. However, using the number 2 is just an example. I could just as well have tripled my initial bundle, or even taking away 50%. So I will denote my new bundle with c times x1, and also I need to multiply x2 by the same constant c. If c is 2, I have doubled my bundle. I've doubled the amount of each good in the bundle. We do the same thing to the y bundle. So if I double my x bundle, I need to double my y bundle. So this new bundle will be denoted by c times y1, c times y2. All four constants c are the same. And c can be any number now, as long as it's strictly positive. If c is less than 1, well then I'm just taking bundles towards the origin, because then I'm taking away from the bundle. So what needs to happen when preferences are homothetic is that I need to be indifferent between these two new bundles as well. So cx1, cx2, I need to be indifferent between that one, and cy1, cy2. If I add here a then, And then for all c greater than 0, then the definition is complete. Take any two bundles, an x bundle and a y bundle, for which I'm indifferent between them. Then it must be the case that I'm indifferent between twice the x bundle and twice the y bundle. I need to be indifferent between 3 times the x bundle and 3 times the y bundle, and so on, and this needs to hold for all constant c greater than 0. So this is a perfect valid definition. However, restrictions on preferences tend in general to be described in terms of the weak preference relation rather than the indifference relation. So it's actually more common to see the following definition. For any two bundles in which the x bundle is weakly preferred to the y bundle, if it is then the case that cx1, cx2 is always weakly preferred to cy1, cy2 for all c greater than 0, then we say that preferences are homothetic. You can use the indifference relation or the weak preference relation. It makes no difference. The definitions are exactly the same. However, I think it's easier to understand the definition when it's described in terms of indifferences instead of in terms of weak preferences. It makes the graph much easier to draw and to understand. Let's add our definition of homothetic preferences to our PowerPoint presentation. Consider two arbitrary bundles, x1, x2 and y1, y2, where the x bundle is weakly preferred to the y bundle. Preferences are homothetic if it is then always the case that cx1, cx2 is weakly preferred to cy1, cy2 for all strictly positive constants c.